So going to go over the sample departmental final exam, and this is very similar to what the exam that you will take final exam for the course. It's always a departmental exam. Any questions before we start? So the exam always consists of 20 small questions, and I've uploaded the exam to Blackboard. If you want to just take a look at it for a second, let me see if we can do this. So this is what the exam looks like. It's posted on Blackboard. And I'm going to go through the questions right now. So there are 20 questions, and problem 1, we have the function y equals square root of 5 plus x to the 5th over 5 minus 5 log x, and we want to find dy dx. The derivative of a constant is 0. The derivative of x to the 5th is 5x to the 4th over 5. The derivative of log x is 1 over x. So we get x to the 4th, the 5's cancel, minus 5 over x. And as I go through the questions, if you have a question, just please interrupt and ask. Unmute yourself and ask. Problem 2, we have a function p of y equals 2y plus 3 over 7y plus 5, and we want to find the derivative. So in this case, y is the variable. It's no big deal. This is a quotient. So you use the quotient rule. The denominator of the function is squared in the derivative. And then the numerator of the derivative is the derivative of the numerator, 2y plus 3, which is 2, times the denominator, minus the numerator, times the derivative of the denominator. So we get, this is all over 7y plus 5 squared, 14y plus 10 minus 14y plus 21. So 10 minus 21 is minus 11, or 7y plus 5 squared. That's the answer. Problem 3 is to write down the tangent line to the graph of the function y equals 1 plus 2 e to the x at x equals 0. So we want the tangent line to this curve at the point x equals 0. And the tangent line is given by, well, you have to know the derivative. What is dy dx? The derivative of 1 plus 2e to the x is 2e to the x. And if you evaluate that at x equals 0, you get 2e to the 0, which is 2. So the slope of the tangent line at x equals 0 is 2. So the tangent line is given by y equals the derivative, the slope, 2 times x minus 0, plus the value of the function at 0. Y, when x is equal to 0, is 1 plus 2 equals 0, which is 1 plus 2, which is 3. So the equation of the tangent line is y equals 2x plus 3. Problem 4, we also want to find a tangent line to a curve. The curve is given by the equation 5x squared plus 3y squared plus xy equals 15. And we wanted to find the tangent line at the point -1, 2. And you can just check. When x is -1 and y is 2, you get 5 times -1 squared plus 3 times 2 squared plus -1 times 2. That's equal to 5 plus 15, plus 12 minus 2. 17 minus 2 is 15, so that checks. So this point definitely lies on the curve. You want to find dy dx. The slope of the tangent line is the derivative at x equal -1. We have to use implicit differentiation. So if you differentiate with respect to x, you get 5 times the derivative of x squared with respect to x, which is 2x, plus 3. The derivative of y squared with respect to x is the derivative of y squared with respect to y, which is 2y, times dy dx. The derivative of xy with respect to x, by the product rule, is the derivative of x with respect to x, which is 1 times y plus x times dy dx. That's all equal to a constant function, 15. The derivative of the constant is 0. So we have 10x plus y plus 6y plus x, or x plus 6y, dy dx equals 0. So dy dx is minus 10x plus y over x plus 6y. And if you evaluate this at the point xy equal to -1, 2, this is minus 10 times -1 plus 2 over -1 plus 6 times 2. That's equal to, see, minus 10 plus 2 is -8. The minus 8 is 8 over -1 plus 12, which is 11. So the slope of the tangent line is 8 over 11. Right? Is there a question about that? Okay. So that's the slope of the tangent line. So what is the equation of the tangent line? It's the line through the point -1, 2 with slope 8 over 11. So y is equal to 8 over 11 x minus -1 plus 2. When x equals -1, this is 2, and this is the equation of the line. This is 8 over 11x plus 8 over 11 plus 2, which is 8 over 11x plus 8 over 11 plus 22 over 11 is 30 over 11. So if I did my arithmetic correctly and the implicit differentiation correctly, that's the equation of the tangent line. Okay. Good. Continuing with the review, we're up to problem 5. So compute the derivative dy dx of the function dy dz, dw dz. W is a function of z, is the square root of 1 plus z e to the z, or 1 plus z e to the z to the power half. So by the chain rule, dw dz is 1/2 1 plus z e to the z to the minus a half times the derivative of 1 plus z e to the z. The derivative of 1 is 0. When we differentiate z e to the z by the product rule, the derivative of z is 1 times e to the z plus z times the derivative of e to the z, which is z. So we get what? We get, in the numerator, I can factor out e to the z. I have 1 plus z e to the z over 2 times the square root of 1 plus z e to the z. So that is the derivative. Okay. Problem 6 is to calculate a limit as theta goes to 0 of 3 times the sine of 4 theta over 5 theta. And what we recall is the basic limit of sine theta over theta as theta goes to 0 is 1. So the limit of sine of 4 theta over 4 theta, same angle as theta goes to 0, is also 1. But in this problem, I have 4 theta, but I don't have a 4 theta in the denominator. But I can adjust that just by doing some simple arithmetic. This is 3 times the sine of 4 theta, 5 theta. If I want 4 theta in the denominator, I can multiply the denominator by 4, but then I have to multiply the numerator by 4. So what I have is 3 times 4 over 5, 12 over 5. The limit of sine of 4 theta over 4 theta, theta goes to 0. And this limit is 1. So this is 12 over 5. That's the answer. Okay. After problem 4 came 5. After 5 came 6. So we're now up to problem 7. This is another limit as x goes to 1 of x squared minus 4x plus 3 over x squared minus 1. And you can't just plug in x equal 1, because you would get 0 over 0, which isn't defined. But you notice these polynomials factor. X squared minus 1 is x minus 1 times x plus 1. And x squared minus 4x plus 3 is x minus 1 times x minus 3. So this is the limit as x goes to 1 of x minus 1 times x minus 3 over x minus 1 times x plus 1. And these x minus 1s cancel. So this is the limit as x goes to 1 of x minus 3 over x plus 1. And now we can't just plug in x equal 1. When x is 1, we get 1 minus 3 over 1 plus 1, which is minus 2 over 2, or minus 1, which is the answer. Okay. Problem 8 is to find the limit as x goes to infinity of 6x squared plus 100 over 7x squared minus 100. When you have a ratio of polynomials that is a rational function, polynomials in the numerator and denominator of the same degree, as x goes to infinity, the limit is just the ratio of the highest degree terms. One way to see that is if you can take the limit as x goes to infinity. If I factor in x squared out of the numerator, I get 6 plus 100 over x. If I factor x squared out of the denominator, I get 7 minus 100 over x. The x squareds cancel. As x goes to infinity, 100 over x goes to 0. So this limit is just 6 over 7. That's the result. Okay. All right. Problem number 9, for which constant k is the following function q of x continuous, and justify your answer. So this function q of x is defined separately for x less than or equal to 0 and x greater than 0. When x is greater than 0, it's the cosine. Cosine is like that. And x squared plus k, well, depending on what k is, that's a parabola, and it hits the x-axis at k. So this parabola for x less than 0, it's equal to 0, it's equal to k at 0. But for the function to be continuous, it has to equal 1 at 0. These two functions can't have a jump. So for what constant k is this function continuous? The constant k equal to 1. That's the unique value of k where this parabola approaches exactly the cosine as x goes to 0. So as x goes to 0 from the right, the cosine approaches 1. As x goes to 0 from the left, x squared plus k approaches k. So for the function to be continuous, k has to equal 1. So k equal 1 is the answer. Any questions about any of these so far? Problem 10 is to use the definition of the derivative to show that if f of x equals 1 over x, then f prime of x is minus 1 over x squared. So the definition of the derivative, f prime of x, is the limit as delta x or h, whichever you prefer as a variable, f of x plus h minus f of x over h. So our function f of x is 1 over x. So this is the limit as h goes to 0 of 1 over x plus h minus 1 over x over h. So we have this expression, which we need to simplify. So 1 over x plus h minus 1 over x. If we put this over a common denominator of x times x plus h, this is x minus x plus h. The x's cancel, I get minus h over x times x plus h. And if I divide all this by h, the h's cancel, I just get minus 1 over x times x plus h. So this becomes the limit as h goes to 0, minus 1 over x times x plus h. As h goes to 0, you just get minus 1 over x times x, or minus 1 over x squared. So that is using the definition of the derivative. This is very important. That's the definition of the derivative to calculate explicitly the derivative of 1 over x. Okay. All right. Problem 11. We have a cube. That's my cube. And the side is S. So the volume V of a cube of side S is S cubed. And the rate at which the volume is increasing, dV dt is 120 cubic inches per second. That's the rate at which the volume is increasing. So dV dt, but V is S cubed, so that's the same as the derivative with respect to t of S cubed, which is the derivative of S cubed with respect to S ds dt. So that's 3s squared ds dt. And dV dt, we're told, is 120. So the rate at which the side is increasing is 120 over 3s squared, or 40 over s squared. And we want to know how fast is s increasing when the volume is 8. So V equal s cubed. If the volume is 8, then s is 2. 2 cubed is 8. So the volume is 8 when the side is 2. So when the side is 2, evaluate this at s equal 2, you get 40 over 2 squared, which is 40 over 4, or 10. So the side of the cube is increasing at a rate of 10 inches per second when the side is equal to 2, when dV dt is 120 cubic inches per second. So this is a related rate problem. The volume and the side of a cube are related by this equation. So dV dt is 3s squared ds dt. So if you know dV dt, you know ds dt, and conversely. Okay. Any questions about that? Okay. Problem 12. We have the curve y equals x cubed minus 6x squared. It's a cubic curve with a positive coefficient for x cubed, so cubic curve always looks like that. And there's usually a point, this is the inflection point. To the left of it, this curve is concave down. And then to the right of it, the curve is concave up. And we want to find where is the curve concave down, where is it concave up, where is the inflection point. So we need the second derivative. The first derivative is 3x squared minus 12x. So the second derivative is 6x minus 12, which is 6 times x minus 2. And what can we say about this? This is positive when x is bigger than 2. So that's where the curve is concave up. And it's negative when x is less than 2. So that's where it's concave down. And the inflection point occurs when x is equal to 2. And when x is 2, y is 2 cubed. X is 2. When x is equal to 2, y is 2 cubed minus 6 times 2 squared. That's 8 minus 6 times 4, which is 8 minus 24, or minus 16. So that's the inflection point. This is the point 2 minus 16. And here the curve is concave up, and here the curve is concave down. So finding the concavity up and down and the inflection points requires the second derivative. Problem 13, f of x is x to the fourth minus 4x squared plus 2. And we want to find the relative extrema. Again, this is a fourth degree polynomial. Fourth degree polynomials usually have curves that look like this. So we would expect 2 local minima and 1 local maximum. Let's see. The first derivative is 4x cubed minus 8x squared. That's 4x squared times x minus 2. So this is equal to 0 at x equals 0 and x equal 2. So these are the critical points. What is the second derivative? The second derivative is 12x squared minus 16x. So that's equal to 12x times x minus 16 over 12, which is 4 over 3. That's the second derivative. So f double prime at 0 is 0. F double prime at 2 is 12 times 2 times 2 minus 4/3. That's positive. So, very interesting. So at x equal 2, the second derivative is positive. So x equal 2 is a local minimum. Right? We have x to the fourth minus 4x squared plus 2. We differentiate it, we get 4x cubed minus 8. Oops, I'm sorry, I made a mistake. I'm glad I did. Minus 4x. That's what it is. 4x cubed minus 4 times 2 minus 8x. So I factor out an x. Let me just erase this and do this correctly. I was suspicious because my second derivative at one point was 0, and the second derivative test is inconclusive there. So x to the fourth minus 4x squared plus 2. The derivative is 4x cubed minus 8x, which is 4x times x squared minus 2. 4x times x squared minus 2. So that's 4x times x minus the square root of 2 times x plus the square root of 2. And the second derivative is 4 times 3, 12x squared minus 8. So f double prime at 0 is minus 8, that's negative. So x equals 0 is a local maximum. F double prime at, what are the critical points? Where this is 0, plus or minus root 2 and 0. At plus or minus the square root of 2, I get 2. When I square this, I get 2. 2 times 2 minus 8 is minus 4. Oops, let's see. F double prime of 0 is minus 8. Again, something isn't good here. So this says x equal plus or minus square root of 2. You have a negative second derivative, so you have a local maximum. So x to the fourth minus 4x squared plus 2, 4x cubed minus 8x, which is 4x times x squared minus 2, 4x, x minus root 2, x plus root 2. So that's the second derivative. And so from the second derivative, the critical points, the points where the derivative is 0, are x equals 0 or plus or minus the square root of 2. If I differentiate another time, a second time, I get 12x squared minus 8. When x is 0, f double prime of 0 is minus 8, which is a local maximum. Oh. When I compute this as square root of 2, this isn't 2, this is 12x squared. So this is 12 times 2 minus 8, which is 24 minus 8, which is 16. So when you have a positive second derivative, we have a local minimum. So now I have the correct answer. For this quartic fourth degree polynomial, there's a local maximum. This is at 0. And we have local minima at plus or minus root 2. So those are the relative extrema. A relative maximum here, relative minimum here, relative minimum there. Any questions about that? In problem 14, we want to find the absolute maximum and minimum values on the interval from -1 to 1, where the function f of x equals 4x cubed minus 3x squared. So we have to find the critical points. F prime of x is 12x squared minus 6x. That's 6x times 2x minus 1. And this equals 0, and x equals 0, and when 2x minus 1 is 0, x is a half. So we have to evaluate the function at the critical points and at the endpoints of the interval. So we have the endpoints -1 and 1, and the critical points are 0 and a half. So let's make a little table, x and f of x. -1, 0, a half, and 1. So when x is -1, this is -4, -3 is -7. When x is 0, this is 0. When x is a half cubed is an eighth. Let's see, so let me just write this down. F of a half is 4 times a half cubed minus 3 times a half squared. That's 4 times an eighth minus 3 times a fourth. That's a half minus 3/4, which is minus a fourth. And when x is 1, this is 4 minus 3, or 1. So if I look at these values, the largest is 1. The smallest is -7. So the absolute max occurs at the endpoint of this interval. It's 1. And the absolute min occurs at the other endpoint of the interval, -1. And the absolute minimum is -7. That's the answer. Okay. Any questions about that? So that was problem 14, which means the next problem is problem 15. Problem 15, a particle is moving along the x-axis with an acceleration a of t equal to 6t plus 2, where t is measured in seconds and s position is measured in meters. The initial position, s of 0, is 3, and the initial velocity is 4. So find the position of the particle at t seconds. So the acceleration is 6t plus 2, and the velocity is, and the acceleration is the derivative of the velocity, which means the velocity is the antiderivative of the acceleration. So it's the integral of 6t plus 2. And the integral of 6t plus 2 is 3t squared plus 2t plus a constant. And what is the constant? Well, v at 0 is 0 plus 0 plus c is 4. So the constant is equal to 4. So my velocity, v of t, is 3t squared plus 2t plus 4. But velocity is the derivative of the position. So the position is the antiderivative or the integral of the velocity. So that's the integral of 3t squared plus 2t plus 4 dt. When I integrate, I get t cubed plus t squared plus 4t plus a constant. And the position when time t is equal to 0, that's c, and I'm told that position is equal to 3. So the constant is 3. So the position at time t is t cubed plus t squared plus 4t plus 3. So that is the position of the particle at t seconds for any t. When t is 0, it's 3. If you differentiate, 3t squared plus 2t plus 4, the derivative, the velocity at time 0 is 4. And the acceleration as the second derivative is 6t plus 2. So this checks. All right. That's problem 4. Sorry, that's problem 15. Let's look at problem 16. So for problem 16, we have a rectangular poster, or a rectangular poster is to have an area of 100 square inches. So we want some poster. So the area is 100 square inches, inches squared, with a 1-inch margin on the right and left sides. So this margin is an inch on the right and the left. Oh, sorry. We have 100 square inches of paper. And we want to have a printed area in that. That's the printed area. So we have an inch on each side for a margin and 2 inches above and below for the margin. So this is 2 inches, this is 2 inches, this is 1 inch, and this is 1 inch. And the question is, find the dimensions of the poster with the largest printed area. So let's say the printed area is X and Y. So, but of course, if this is X, then the width of the paper is X plus the margins, X plus 2. And if the height of the printed region is Y and you have a 2-inch margin on top and bottom, this side is going to be Y plus 4. So we have a piece of paper whose total area is base times the height. The area is X plus 2 times Y plus 4. And we're told the total area is 100. And we want to choose the dimensions X and Y to maximize the printed area. I call this P, which is just X times Y. So if I take this equation for A, this determines Y as a function of A. If A is X plus 2 times Y plus 4 is 100, then Y plus 4 is 100 over X plus 2. So Y is 100 over X plus 2 minus 4. And so the printed area P, it's the height, it's the width X, times this height, which is 100 over X plus 2 minus 4. If I wanted to put this over a common denominator, this is 100 minus 4 times X plus 2 over X plus 2, which is 100 minus 8, 92 minus 4X over X plus 2. So this is X times this, 92 minus 4X times X over X plus 2. That's the printed area as a function of X, and I want to maximize the printed area. So let me just go through again how I set this problem up. We have a rectangular poster with a total area of 100 square inches. So this poster is going to have 100 square inches. And you're going to print on that poster, but you have to leave 1 inch on the left and the right for a margin, and 2 inches above and below for a margin. So if the dimensions of the rectangle that you're printing are X and Y, then the width of your paper will be X plus 2, and the height of the paper will be Y plus 4. And X plus 2 times Y plus 4, that's the area of the whole poster, that's 100. So Y plus 4 is 100 over X plus 2, or Y is 100 over X plus 2 minus 4, which is 100 minus 4X minus 8, or 92 minus 4X over X plus 2. So the printed area is X times Y, it's X times that. And I want to maximize that. So what value of X maximizes this? We have to differentiate. dP dx is equal to what? This is X plus 2 squared. The derivative of the numerator, let's see, what is this? This is 92X minus 4X squared over X plus 2. If I differentiate the numerator, I get 92 minus 8X times the denominator minus the numerator times the derivative of the denominator, which is 1. So this is what is this? Let me expand all this. So over x plus 2 squared. I have 92x plus 92 times 2, which is 184, minus 8x squared, minus 16x, minus 92x, plus 4x squared. The 92x's seem to cancel. I get 4x squared minus 8x squared, that's minus 4x squared, 184 minus 16x minus 4x squared over x plus 2 squared. Let me write this down again. So dp dx is 184 minus 16x minus 4x squared over x plus 2 squared. Let me just factor a 4 out. So this is, I'll put a minus on it. I like my, right? This is minus x squared plus 4x minus 184 over 4 is 4 into 18 is 46. Over x plus 2 squared. And 4 into 18 is 4. 4 into 24 is 6. Yeah. So something about this doesn't look right. So I just want to go back and double check what I did. So we have a rectangular poster. Oh, I see. There's this sort of ambiguity here. Wait a minute, no. A rectangular poster is to have an area of 100 square inches with a 1-inch margin on the right and the left and a 2-inch margin on the top and bottom. Find the dimensions of the poster with the largest printed area. So if the printed area has dimensions x and y, the poster has dimensions x plus 2 and y plus 4. So x plus 2 times y plus 4, that's the area of the rectangular total poster, is 100. So y plus 4 is 100 over x plus 2, or y is 100 over x plus 2 minus 4, which is 100. So y is 100 over x plus 2 minus 4, or I can factor out a 4 if I like, 4 times 25 over x plus 2 minus 1. And the area of the poster, x times y, is 4 times 25x over x plus 2 minus x. So if I differentiate this, p prime of x, this is 4 times, I have x plus 2 squared, the derivative of the numerator, 25 times x plus 2, minus 25x times 1, minus the derivative of x, which is 1. So this is 4 times, I have 25x minus 25x, 50, I have 50 over x plus 2 squared minus 1, and I want that to equal 0. So that equals 0 when x plus 2 squared, when 50 over x plus 2 squared equals 1, or x plus 2 squared equals 50. So x plus 2 is the square root of 50, which is 5 times the square root of 2. So x is 5 root 2 minus 2. And if x is 5 root 2 minus 2, y is equal to 100 over x plus 2, which is 5 root 2 minus 4. This is 25 over root 2 minus 4, which is, if I want to write it that way, well, that's what it is. And the printed area, P, which is x times y, is 5 root 2 minus 2 times 100 over 5 root 2 minus 4. If I multiply this out, I get 100 minus 20 root 2 minus 102. So this is just 20, of course, 100 over 5. Minus 40 over root 2 plus 8. So this looks like 108. This is 40 root 2 over 2, which is 20, minus 40 root 2. So that's interesting. So this was a little complicated, more complicated than I would expect. So I'm just going to go through it again and try to make this clear. So this is problem 16. We have a piece of paper, a poster, and the total area is going to be 100 square inches. And we're going to draw a poster here. We're going to print, but we have to give ourselves 2 inches top and bottom and 1 inch on each side for a margin. And so we have this printed area inside the poster, and we want to choose the dimensions of the poster. So the total area is 100, but we maximize the area of the printed part. So if this printed part has width x and height y, the area of the piece of paper, the width of the piece of paper is x plus 2, and the height is y plus 4. So x plus 2 times y plus 4 is going to be 100. So y plus 4 is 100 over x plus 2, or y is 100 over x plus 2 minus 4. So the printed area P as a function of x is x times y. That's, multiply this by x, 100x over x plus 2 minus 4x. If we differentiate this, we get 100. Let's see, I have x plus 2 squared. And in the numerator, I have the derivative of x, which is 1 times x plus 2, minus x times the derivative of the denominator, which is 1, minus 4. X plus 2 minus x is just 2. So this is 200 over x plus 2 squared minus 4, and that has to equal 0. So 200 over x plus 2 squared equals 4, or x plus 2 squared is 200 over 4, which is 50. So x plus 2 is the square root of 50, which is 5 root 2. So x is 5 root 2 minus 2. And y is equal to 100 over x plus 2. which is 5 root 2, minus 4. 5 over 100 is 20 over root 2 minus 4. Or I can write this, if I wish, as 20 root 2 over 2 minus 4, or 10 root 2 minus 4. And those are the dimensions of x and y. So the width of the paper is going to be x plus 2, 5 root 2, the height y plus 4, 10 root 2. And you can check that the product is 100. It's just what it's supposed to be. So that's problem 16. Problem 17 is to write a Riemann sum for the integral from 0 to 1 of the square root of 1 plus x squared dx, a 3-term Riemann sum. So this goes back to the definition of the integral of the definite integral is an area under the curve. If you have the function f of x equal the square root of 1 plus x squared, what does the graph of this function look like? As you go from 0 to 1. When x is 0, this is square root of 1. As x goes from 0 to 1, this increases to the square root of 2. So this is the point 1 root 2. This is the point 0, 1. We take this interval and we divide it up into 3 equal pieces, 1/3, 2/3. We draw these vertical lines, and we can take, for example, the left-hand endpoint of each interval. This is 0, 1. When x is 1/3, this point has coordinates 1/3, square root of 1 plus a ninth, 1 plus 1/3 squared. That's 10 ninths, or root 10 over 3. When x is 2, so f of 0 is the square root of 1 plus 0 squared, which is the square root of 1, or 1. F of 1/3 is the square root of 1 plus 1/3 squared, which is the square root of 1 plus a ninth, which is the square root of 10 ninths, which is 1/3 the square root of 10. And f of 2/3 is the square root of 1 plus 2/3 squared, which is the square root of 1 plus 4 ninths, which is the square root of 13 over 9, or 1/3 the square root of 13. So this point has coordinates 2/3 root 13 over 3. So a 3-term Riemann sum, you have the area of this rectangle, which is the height, 1, times the base, 1/3, plus the area of this rectangle, which is the height, root 10 over 3, times 1/3, plus the area of this rectangle, where the height is root 13 over 3 times 1/3. So this is a 3-term Riemann sum to approximate the area under the curve by 3 rectangles. That's what it is. In problem 18, we have the function y equals 5 minus 2x squared. This is just a parabola. The vertex is at 5, opening down. Parabola looks like that. And we want to find the area under this curve from 0 to 1. When x is 1, the height of this curve is 3. We want to find the area under the curve. The area is the definite integral from 0 to 1 of 5 minus 2x squared dx. Now, if we let capital F of x be the indefinite integral, the antiderivative of 5 minus 2x squared dx, this is 5x minus 2/3 x cubed. So the area is this antiderivative evaluated at 1 minus this evaluated at 0. When x is 1, this is 5 minus 2/3. And when x is 0, this is 0. And 5 minus 2/3 is 13/3. So that's the area under the curve. Problem 19, we have a function f of x, which is an integral from 0 to x of the function 1 over the square root of 1 plus t cubed dt. And if you have a function which is an integral from a fixed lower point of integration 0 to x of some function, the fundamental theorem of calculus says the derivative of this is just the function at x, 1 over the square root of 1 plus x cubed. This is just immediate from the fundamental theorem of calculus. In problem 20, this is an integration to solve the integral of x times sine of x squared dx. Let me write this as the sine of x squared times x dx. Now, if I let u equal x squared, du dx is 2x. I don't have 2x here, I have just x. But if I multiply and divide by 2, this is okay. And now I have 1/2 sine of x squared 2x dx. That's the integral of sine of u du. That's substitution. The integral of sine u is minus the cosine of u plus a constant. So that's minus 1/2 the cosine of 2x plus a constant. And that, lo and behold, is the whole review sheet. Any questions about this? I think what I'll do actually is find another old exam that I'll post on Blackboard as an additional review set, and I'll go over that on Monday next week. Any questions about this, what we just did? So I remind you the final exam is Monday. Sorry, not Monday. The last class is Monday. And the final exam, oh, actually the final exam is late. The final exam is a week from Monday. And it's going to be on Pearson MyLab. It's not in person on campus. It's on Pearson. Okay, that's all. If there are no questions, let me see something in the chat. Yes, okay. Oops, no, that was something else, but okay, that's to right, that's done. Okay, we're done for today. Be well all.